I would like to say to everyone in Taiwan, the management had banned Zoom. In fact, we have internet issues, Zoom problems.
Mm-hmm.
Okay. Yes. I can start it. I can start. Okay, Professor.
Yeah.
Okay. Okay. Yes, I'm opening third session. Firstly, I would like to thank Professor Jacky Baltes. I'm so glad that you are joining us for workshop. Many thanks. Firstly, I would like to introduce Professor Jacky Baltes. We prepared a video I will share. Sorry.
Shooting.
Yeah, me too. I also.
Okay, I can stop.
I also cannot see anything but my screen. Your title screen. I do not actually see the video.
Okay, okay, I will open.
And I think one of the participants just said the same thing.
Yes. Okay. Okay. I opened your presentation.
Yeah, I think we just open my presentation and then we hope that it will play the videos correctly. I'm very curious to see what video you created about me. So please send me a copy so I can see it sometime. I only saw your main screenshot with the itinerary. But if you want to, then I can start now.
Yes, please.
That's the idea. Okay, good. Yeah. So welcome and thanks for joining me here. My name is Jacky Baltes. I'm a professor at the National Taiwan Normal University in Taipei, Taiwan. And if we go to the next slide, I'd like to introduce my research to you. So my main, and this is really the why of the presentation, why we're doing things. We're doing the projects that I will describe in the future because I'm interested in human and artificial intelligence. My degree was in computer science, AI, a multi-strategy planning system. And I've been fascinated by it. How can humans think? How can they solve these very complex problems in the real world? And when I started my first job as a young professor at the University of Auckland in New Zealand, I realized that a lot of the AI research, which is only based on simulation, is really based on wishful thinking. And that a lot of the problems that we consider to be trivial turn out to be very, very hard if you want to do them with a real computer, with a real robot. And some of the things that interest me since 2002 are walking on two legs, which is a challenge for humanoid robots, active balancing, walking up a slope, walking over uneven terrain or through a forest is a very difficult problem. And then also push recovery balancing when the robot is being knocked by another robot or a human or an obstacle in the environment. Secondly, I'm interested in complex motion planning. Humanoid robots have many degrees of freedom, which means that they have an almost infinite possibility of actions that they can perform. Only some of them are going to be useful, and they have to obey dynamic constraints and stability constraints. And so, for example, for robot soccer, you really only need about a dozen motions. You need to walk forward and backward. You need to turn left, turn right, and shuffle left, shuffle right. You need to be able to kick with your right foot. You need to be able to kick with your left foot. And then if you fall down, you need to be able to stand up again. So those motions I can give to any one of my, if you go back to the previous slide, those motions need to be developed. They can be, if you only have a dozen, you can develop them. I can tell my graduate student to create those motions for us, parameterized motions, so we can vary the step height or how much we turn to the left, how much we turn to the right each step. But humans are very good at creating motions on the fly. And that's really one of the very interesting, most fascinating aspects of human reasoning that is really not very well understood. And lastly, I'm also interested in human-robot interaction. How can we make the robot understand human speech and human gestures? And how can we make the robot generate intelligent, meaningful human speech and human gestures? How can we teach a robot how to perform various tasks? And so for many years, I've been interested in robot competitions as a benchmark problem for AI research. So if you could now go to the next slide, please. So that's the why we're doing this. Our humanoid robots I will introduce next. So this will be the who is doing it. The research interests that we have with these specific robots and challenges, the what we're doing, I will describe. And I also give a high-level description of the how. But for the details of a lot of these algorithms, you will have to look up our papers. And then I will summarize the talk with our contributions. If we go to the next slide, I'm the director of the Educational Robotics Center at NTNU. We're an international team of researchers. We have visiting professors from Brazil and Iran and Germany and France. Hopefully in the future, we can have visiting researchers from Turkey as well, or students. I have postdocs from Korea and Taiwan and Indonesia. We can go to the next slide, please. So we have several of the Darwin OP robots. Those are actually made by a company in Korea. They are 45 centimeters tall and have 22 degrees of freedom. And they've been quite successful at the robot competition. So in 2019, they won the FIRA all-round event. And I'll explain in more detail what that is later. Then if we go to the next slide, our larger humanoid robots, 80 centimeter tall Robinion, is heavier, has more degrees of freedom, 26 degrees of freedom. It has articulated grippers, so we have fingers that we can use. With that, it participated in the Eurocup competition and also in the Magic Show. Next. Please, next slide, please. We have a 1.3 meter tall humanoid robot that we built specifically for RoboCup, the adult size category. We did pretty well there, winning a 3rd place as well. And next slide, please. Our largest and heaviest robot is the Thormang, which is also built by a Korean company, Robotis. 42 kilograms and 31 degrees of freedom with more powerful processing and more powerful sensing. In particular, it includes laser scanners. And that robot also was successful at the Robot Magic competition. If we go to the next slide, please. So for me, robustness and versatility are important aspects of intelligence, maybe the fundamental aspects of intelligence. But humans are actually pretty bad at solving problems optimally. If you consider playing chess, which was one of the standard problems for AI, then it took until 1996 until we developed a computer program to beat the human world champion in chess. In that specific domain, that was possible. What to me was even more interesting was that any one of my students in 1990 could have written a chess playing program that can beat 80% of the people in the world playing chess. Not because my students are supremely smart, but just because most people are very bad at playing chess. It's not one of the things that our human intelligence allows us to do very efficiently. However, we still don't have computer systems that can match human perception. So when your 3-year-old nephew detects the mother and father and walks into a room and says, "Oh, Uncle Joe, I'm glad that you're here," that's already outperforming the best computer vision systems that we have in the world. So our robots can outperform humans if it's a very specific task. So in machine vision, we can detect if a drill hole in an airplane part is off by a millimeter, something that humans would not be able to do. Or robots can do pick and place tasks for a very specific motion path very, very quickly, faster than humans could do. But robots will also walk into a wall, not just once or twice, but 3 times in a row without thinking anything about it. And one of the issues in the research is that paper and video, in a sense, are patient. I can take a video of my robot if I want to demonstrate that my robot can score a goal or kick a ball, then even if I try it 100 times and it works one time, then I can post that particular video. But in robot competitions, we can't do that. Robustness is a very important feature of our robots, and so is versatility, because the playing fields are never the same. We cannot fine-tune for the exact kind of carpet that we have in our laboratory. We have to go to, it was in Changwon in Korea. Next year, we hope to be able to go to Brazil. And then we have to deal with the environment there. And then at 9 a.m., the referee is going to blow the whistle, and your robot has to be able to perform. And he has to be able to do 5 trials successfully if you want to win the competition. So if you go to the next slide, please. So for us and several other researchers throughout the world, we think that combining sports and robotics is a very natural way to motivate both teams and spectators. For example, I will tell you later on that in this particular Euro Cup competition, we have a sprint event. Just by saying that we're doing a sprint, you already have a pretty good idea of what research we're trying to do. We want to do how fast the robot can walk on a short distance. And if I tell you we're doing a marathon, then it's clear that we're attempting to improve the endurance of the robot. So the Federation of International Robot Sports Association, FIRA, has several leagues for robot athletes. We had the World Cup, successful one in 2019, and the next one will be in Brazil. We go to the next slide, please. Oh, how come your images don't load?
There is no image.
There is on my browser. Okay, so FIRA includes several leagues. For participants, I just posted the link in the chat, so you can actually follow along with the presentation. Hopefully the images show up for you. I don't know why they don't show up in that browser. That's a little bit strange, but okay. So we have several leagues. There's a large category, many teams participating in the humanoid robot competition, the Euro Cup. We also have a global vision competition where there's a camera mounted on the ceiling and humanoid robots are playing soccer against each other. That's called Androsot. We have a league for drones. We have a league for wheeled robots. And also several application-based leagues that are focused on wheeled robots in an industrial setting. So if we go to the next slide then. The FIRA Euro Cup, when it comes to humanoid robot research, then again, we're interested in flexible, robust, versatile solutions. So if you are working on a single task, then usually you will never end up with a humanoid robot design. The reason is that if you want to deliver mail in an office, you build something with wheels that can drive around and a laser scanner, and it'll do a much better job than any humanoid robot possibly could. If you want to walk up stairs, then you can have a track design to do the same thing. If you want to clean the window, then you can build something with suction cups and a wiper. And if you want to wash the dishes, then you build a dishwasher. So for a single task, you wouldn't really end up with the humanoid robot design. You only end up with the humanoid robot design if you want to have a single robot that can perform all of these tasks and many, many more. And that is sort of similar to how humans are located in the animal kingdom. If you think about it, humans aren't the best at running. Cheetahs can run much faster than us, and we aren't the best at climbing. Monkeys are much better than us. And dolphins are much better swimmers than us. But humans are unique in that they are in the top 5 in basically everything. So although we're not the best climbers, we sure can climb a lot better than any dolphin ever could. And so because of that, we designed this Eurocup as a decathlon where a single robot has to compete in 10 different events: the archery, the sprint, the marathon, the obstacle run, the soccer competition, the triple jump, a Spartan race, which is sort of an extreme obstacle run, which includes uneven terrain, ladders and ropes that the robot has to climb, weightlifting, basketball, and the mini DRC, which is basically a disaster rescue robot that is teleoperated. And all of these applications, in the future, we would like to build robots that can do rescue work. But if we just test that now, put a house on fire and send in 10 robots, and none of the robots will be able to come out. So we need to have intermediate steps. We need to have intermediate goals that we can achieve that show us that we're progressing, by how far we are progressing. So if we go to the next slide then. Okay, there's another picture now missing, so this is not going to work then. The picture shows up fine on my machines. Oh, okay.
See. Oh.
Okay, let me try if I can share my screen, but I'm not sure. Oh, am I still there? Okay. Google Drive, photo, web URL. Okay. Did I misspell it? Clear text not permitted. Oh. Oh. Stop share. Share. No, not space. Okay, or maybe you could ask the participants if they can access the presentation with the images.
Images.
Yeah.
Well, how? I can.
If the participants, if they're can check that URL that I posted at the beginning, click on it, and then they can follow along the presentation. Then we don't have to. Then if you don't show the images, then it's not a big problem.
Yes. Yes.
Okay, so now I think I'm sharing something. Because there's a lot more images coming, so okay, it's still loading for me now.
Image. I can't see image.
And my browser here won't.
Browse.
I can copy.
I think that you sent me your image, but I can't see your image.
No, the presentation is not ended yet. OneDrive, folder doc. Whiteboard, no.
Where is the image? I can't see.
Yes, I can see that you cannot see it. We need to tell the participants to go to this web page on their browser, and then they should be able to see the image. And did you use HTTP or HTTPS?
Interesting.
Oh, maybe.
I tried multiple browsers, Microsoft Edge and Mozilla. I used difference?
No, I think maybe a problem with HTTP versus HTTPS, but okay, then they won't be able to see the images. Hopefully the videos would show up. Can you go to the next slide then, please?
Okay.
Okay, yeah, we did that one. And next slide, please.
Here?
Okay, now if you click on the video, at least we can see the video. So the weight.
Can I continue?
Pardon?
Can
No,
I...
no. Yeah, continue with the video. But mute the sound. You turn the sound off.
Yes. We turned.
Yeah, okay, good. Then we can see the robot. So for the weightlifting, it's basically a balancing problem. The robot has to walk up to the weightlifting bar, then move ahead 50 centimeters with the weight low. So now the center of mass of the robot is very low. Now it needs to lift up the weight above its head, which requires proper synchronization between the arms and the legs and the torso. And then it has to walk another 50 centimeters. Now the center of mass is much higher. So it's more difficult for the robot to do that and still maintain the navigation ability. Like it still needs to be able to walk at least sort of straight. So this is one of the events that we have in EuroCup. We can go to the next slide.
Next slide.
Yes, please. So then we also have a sprint competition. If we go to the next slide, and if you start the video and then mute the sound.
There is no video.
Next slide.
Next slide.
Yeah,
No.
and then start the video and mute the sound. Yeah. So in the sprint, the robots have to walk 3 meters forward and 3 meters backwards. So this is a pure burst of speed kind of event. One of the nice things about using sports for AI research benchmark problems is that we can easily see the progress. So 2012, the world record in this event was 1 minute and 12 seconds. And 2018, a team from Indonesia did it in 23 seconds. So you can see how much the robots improve every year, even though we make the challenges more difficult. And now you can turn on the sound from the video, please, because it's actually quite exciting now. Every time the robot steps out of line or falls down, cannot stand up, they have to start from the very beginning. So we can go to the next slide. Yes, we also have a soccer competition. I think we have a video later on coming up. Oh, that shouldn't be there.
Sorry again. Oh, okay.
Yep. So next slide, please.
Okay.
The Spartan race is a very interesting competition because in there you have to walk over an uneven field. You have to climb a ladder, and since 2017, you also have to climb a rope. So my team was actually the first team that was able to climb the rope in this particular competition, and we're quite proud of that. So next one, please. Next slide, please. Yeah, so we have a penalty kick competition as well, and an obstacle run. Next slide, please. Next slide, please. Yeah. Okay. Too many. So in the marathon is exactly what you expect, an endurance race, 425 meters, 1/1000th of the human marathon distance. It's held outdoors, so it's an advanced vision problem because you need to deal with sun and shadows. And the robot has to follow a track and markers. So there's arrows pointing to the left, to the right, and up, forward, to tell the robot where it should walk, where the path is that they need to follow to complete the 425 meters. Next slide, please. There's a triple jump competition, which is mostly motion synchronization, a very highly dynamic motion. And you also need to land the robot after your jump. It's done on a table, and the robot just has to jump 3 times in a row. And again, some of the teams have come up with surprising solutions. The world record right now is from a team in Malaysia. They jumped 67 centimeters or something like that, which was truly phenomenal. It was much bigger than the organizers expected, so they had to get a bigger table. That team decided that they were not interested so much in the all-round competition. So each one of these events that I described, you get points. And then at the end of the competition, the King's Crown is the team that wins most points overall, just like in the decathlon. So that makes it a very challenging, very interesting system design problem, because you need to think about your battery, for example. In the sprint, you want to run very fast, and you only need power for 23 seconds, so you want a very light battery. But in the marathon, you need to run a very long time, so you need to have a higher capacity, which is usually heavier battery. But you're not allowed to change the battery from one event to the other. So you have to think very carefully about what the weakest link is in your competition and how to improve that. So we can go to the next slide, please. Yes, we also have a basketball event. Unfortunately, nobody can dribble at the moment. So it's a dunking event, 3-point shots, basically, and 5-point shots. Next, please. We do archery, and we can go to the next slide, which shows our large robot. And if you play the video, I think that's a video that you played before, anyway. So this is an interesting problem for vision, because we need to detect the targets. and it's an interesting problem for motion control. We need to be able to generate very high accuracy motions, better than 0.4 millimeters. Our goal is to compete at the national championship in Taiwan next year, and then qualify for the university games in 2022. And it would be the very first time that a humanoid robot can actually compete and beat a human Olympic athletes based on rules for humans. Then next slide, please. Oh, that picture shows up. Weird. Okay. So apart from sports, we're also interested in magic. And the reason for that is that attention is a very important part of human perception, but it has so far not received a lot of attention in AI research. And if you look at the image on the right, then if you see a young lady looking away from you, or if you see a grandma looking at you, depends on what you first focus on. So your brain will pick out the necklace or the mouse, and then it will construct the image from what it sees. And then it's almost impossible to switch over to the other perception. And when we ask of computer vision systems, this one-step recognition that we show the image and we expect, bam, car, chair, dog. I want you to identify, label all the things in the image in one swoop, is not really the way that the human vision system works at all. A lot of the things that humans see is mostly what they expect to see. And magic is very good test bed for ideas in attention, because magic, in a sense, is all about misdirection of attention. I want you to look at my right hand, but the trick is really happening in my left hand. So if we go to the next slide, please. So we have the robot magic show. Yeah, these pictures are now okay. Here's the event from 2018 in Madrid, where the robots perform different magic tricks. And I'd like to show two of them from my team. If we go to the next slide. And if you play the video, please. And I think play the sound, because the robot will give the instructions. I'll turn the volume up.
I think I know where it is. Cross your lines in front of you now.
So the robot is trying to guess in which arm the human put the coin. And that has a lot of psychology included there as well. It turns out that most people, if you ask them to cross their arms, they will put the coin in the bottom. And this one, the robot actually guessed correctly. Later, work out how to detect which arm is on top. It's easy to detect the arms, but it's hard to detect which arm is on top of which other arm. And if we go to the next slide, please. So this is a common magic trick behind hide the coin behind the back, and then I guess when you bring out your arms where the coin is. And the next magic trick is a nail trick. So there we included some comedy, so I hope that you can enjoy the audio. The student tells the audience that they've not been successful in their research, so they always place the bag with the nail in the middle of the 3 bags. And they say that in front of me because I do not speak Chinese. So the funny thing is that they can talk all this to the audience without me actually realizing what's going on. So the audience thinks that I think my students are using very sophisticated AI technology in order to detect the bag. But in reality, the students are fooling me every time. So now then we ask the audience to pick bags, and my student tells the audience, please, if I want to graduate, please don't take the middle bag, because if my professor gets hurt, then I will never be able to graduate. And so most audience is kind, so they actually don't take the middle bag. So in this case, we implement a fake robot crash. So it looks like the robot crashes, gets confused, and then tries to put the hand on the middle nail, middle back, which is where the nail is. So that would be very painful. But in fact, the nail magically moved to the right-hand side. And the robot was correct, and all the humans were wrong. So if we go to the next slide, and then please play the video.
Welcome everyone, I am Thorming. Today I am going to show you a magic trick that I have learned recently. As you can see, there are 3 paper bags in front of me. Later, I will put this wooden base with a sharp nail into one of the paper bags, and then swap around the position of the bags. To make sure we won't find out the bag is empty by feeling the weight. So I prepared 2 wooden bases without nails. Student, please help me put these 2 wooden bases into 2 paper bags and close it.
So our research goal here is detection, manipulation of soft, deformable objects, because the paper bag is not solid, so you cannot just squeeze it.
Student, please ask an audience member to examine the nail and make sure it is real.
Now you can check.
看一下这个是真的，这个磨盘是
So, audience volunteer, can you confirm to the rest of the audience that the nail is indeed real?
是真的吗？
Okay, thank you. Student, please place the nail inside the last bag and close it. And everyone, please pay attention and remember which bag contains the nail. Now, I need another volunteer.
Any volunteer?
但是可以站这边就好。
Thank you for volunteering. Now, do you remember which bag contains the nail?
So now we're going to shuffle them, but the robot, because it has very fine vision, it can detect where the bag is, basically.
You mean this one, right? To make sure that I won't be able to know which bag contains the nail, the student will start swapping the bags around. When I say start, the student will begin, and volunteer, you can shout out stop anytime you want.
So you just need to say stop.
Let's start.
Stop.
Okay, now I need some time to feel where the nail is.
因为我们老师他听不懂中文，然后其实我们只有1个礼拜时间可以做这个魔术，所以我们就用机器人知道说，刚刚也看到是在中间没错嘛，那就麻烦等一下的时候帮我们讲左或右。
哦 ，OK。
对，选择的时候，因为他等一下问说哪一个袋子里面没有那个针，铁钉没有铁钉，然后他会让老师去按那个没有铁钉的袋子，所以待会一定不要选中间。
What's so funny? Everything okay?
Oh, I am
The
not
audience is all happy
sure where the nail
for
is.
me.
So I would like to play something. supervisor of your lab. Do you believe in my talent and your students' ability?
Not so much my students' ability, but their hope to graduate, I think.
Oh, I am happy to hear that. Since you trust us so much, we can raise the stakes. How about we use your hand to press down on the paper bags?
I'm not so sure about that. It was supposed to be Green's hand, not my hand.
Please give me your hand, Jacky.
Okay.
Volunteer, choose a bag you think there's no nail inside. Left, right, or middle? Choose wisely. We wouldn't want our dear professor to get hurt, right?
Left.
Okay, left.
Okay. You sure about this? Oh! Okay.
Jacky, don't be a bit nervous, don't you trust me? I am the only hope of graduation for your students.
True.
They won't disappoint you, trust me.
Okay.
Hey, volunteer, what's your next choice?
Right.
Left or right?
Right.
Okay, right.
Okay.
Now, right, really, everybody thinks it's not a nail, but it
Finish
actually is.
your moving.
Oh,
Now
okay.
we make the robot crash.
Okay, this one?
Yes.
Okay.
But I don't think this one is safe. Jacky, do you trust me?
No, not really, no. You just remove it.
Why? I only made one mistake.
Yeah, but you see
Why
my
don't
other
you
hand.
give me another chance?
I only have two hands.
Well, here.
We forgot to put the snap on. That's the
Yeah,
problem.
like you. Ha ha ha. Don't get that scared. I know what I am doing. So you might be really curious where the actual nail is, right?
Other bag.
Jacky, please help me to check what is in the bag.
This is one of our favorite magic tricks that we like to do with the robot. It works particularly well in the country.
So you can
Okay, next slide, please. Can we go to the next slide, please? Yeah. So I will skip a couple of slides now because we're running almost out of time. But you have the URL. You can look at the videos yourself. Next slide. Next slide. Next slide. We'll have to skip a whole bunch of them now. So next. We also play Dr. Eureka, next slide, which is the speed logic game. You get cards and then balls, and you need to pour them from one to the other. It's an interesting dexterity challenge for robots. Then next. Next. Because I really want to introduce our latest and most latest and most ambitious project. Next slide, please. We have to skip that one. Yes. Next. Next. No, one before that. Yeah. So our latest project is to have a humanoid robot drive an electric scooter, which is made by the Gogoro company, and be able to maneuver with it and if everything goes really well, we hope to be able to pass the Taiwanese driver's license test for scooters, which includes several technical challenges. The robot needs to be able to drive at a very slow speed in a straight line, has to cross a railway crossing correctly, has to do a right-hand and a left-hand turn correctly. So we have a scooter in our lab, and if we start the left video now, please.
This one?
The other one. Or actually, that one is okay too, yes. On the left-hand side, you see my students working on accuracy and precision of our control for the steering angle. So we mounted a laser pointer on top of the scooter in order to be able to tell the robot that we need to turn 12 degrees. We need to know that this is exactly 12 degrees, and we need to know how accurate, how precise it can do that. And on the right-hand video, you have a simulation of our robot on the Gogoro scooter. If we started from the beginning, you can see the robot drive off, and then there's a push, and then we use, at the moment, a very simple inverted pendulum model in order for the robot to steer so that he stays balanced on the scooter, which is, of course, one of the challenges that we have with this particular project. So just last week, we added the training wheels. So our real driving tests are going to start sometime in the middle of December, and we're all very excited about this. This is by far the most ambitious and interesting project that we're currently working on. And then I can go to contributions, please.
Okay.
So the technology that we use to achieve these different tasks, we use hot feature detectors. We implemented a visual compass algorithm, developed one for the sprint event, various motion planning for soft objects for the magic show to pick up the bags and the nails and everything. We have a simplified version for edge devices of YOLO 4 and a NN inverted kinematics motion planning system for the Dr. Eureka game. We use deep Q learning to learn how to manipulate a keyboard and type on an arbitrary keyboard. And we've then extended this into automatic defibrillator devices. And also for the Gogoro scooter, we want to apply reinforcement learning so that the robot can learn how to balance on the scooter independent of the exact center of mass of the scooter, for example, or the exact control function of the throttle. And hopefully I have convinced you that meaningful robot competitions are important for inspiration as a test bed and as benchmarks for research in artificial intelligence. And that will now conclude my presentation.
Thank you so much for your valuable presentation, Professor Jacky Baltes.
Could you do me a favor though and just press F11 now to see what it would look like full screen if I have to do this again?
Oh, okay.
Does it not go full screen?
Full screen. Full screen. That's okay?
Yeah, it's okay. Yeah.
Okay. Thank you again. I would like to give your certification. Our Pratt University Director signed your certification. I will send you.
Okay, thank you very much. Yes. I mean, I'm open for questions too. If people want to ask me a question, then they should do that now.
Yes. Do you have a question?
Hello, Professor.
Yeah.
Thank you very much for the wonderful presentation. My name is Bilyamin Muhammad, a student of software engineering from Firat University, Elazığ here in Turkey.
Mm-hmm.
I just want to ask, what is your advice for the researchers like me who want to develop interest in robotic development? Thank you.
I think robotics is all about doing projects, starting from small projects to larger, more complex projects. None of my students started working out on the Thormang robot. Everybody starts with small wheeled robots, but you can do some interesting work with that, even if you don't have many degrees of freedom. But it's important to get an understanding of the whole nature of the physical world. If you ask most roboticists, then if you ask them about the accuracy of their sensors, then most robotics people that have experience, they don't talk about the accuracy. They simply tell you that, oh, our sensors are constantly lying to us. It's our job to try and figure out what the truth is behind all their lies.
Okay.
So I can only recommend that you start building robots, even if they are simple ones. That will teach you the necessary skills that you need to have. Also, one other reason for the students in the audience here, I think robotics is actually very good. And my experience is that robotics is very good because you train excellent problem solvers. You learn to look at a problem from a mechanical engineering point of view, an electrical engineering point of view, and a computer science point of view at a minimum. And then you may also include psychology or philosophy or some other areas. And that is very important, because if the only tool you know how to use is a hammer, then every problem will look like a nail to you. But if you know how to use low-pass filters and linear regression and neural networks, then you have many different tools to actually try and solve the same problem. And you may then realize that actually the latest fancy AI technology is not really suitable, that it could be much easier solved with a capacitor and a resistor in the right place in your circuit, or a redesign of your mechanical structure. So I think that makes robotics trained people very good problem solvers, which is why they're also sought after by companies. So I have lots of companies that contact me about hiring my students. Some of them have had very interesting careers. Brian McKinnon, one of my students, is now one of the developers for Assassin's Creed, which is a very famous computer game. Or Xiaohong Liu, she was the director of motion capture for Lord of the Rings and Avatar movie. And another student of mine is now working as a vice president for the Bank of America. And all of those are, even though they're not really in robotics field anymore, still use the skills and the methodologies and the approaches that they learned in the robotics lab.
Thank you for answer.
Thank you very much.
Do you have any question? Okay, thank you, Professor Jacky Baltes. I hope that we will join RoboCup in next years with my students. Yep. Thank you so much.
Okay, thank you very much.
Thank you.
Bye-bye.
Good evening. Hello to say to your wife.
Yes, I think she walked by in the background here quickly. Yes, yes.
I saw you. See you.
Yeah.
Thank you.
Okay. Okay, thank you. Bye-bye.
Bye-bye.
Okay, thank you, Professor.
See you the other section. In the other section, see you.
Mhm.